So in this video, I'm going to talk about two aspects of optimization. So let me start with maximization. So imagine we have a function. So we're going to let's do a simple one. Define f of x, and we want to maximize 1 minus x squared. So to understand this function, it's probably best just to plot it up. So we do linspace 0 to comma 1000, and then we're going to do plt plot x f of x, line width equals 3, color is equal to red, and then we're going to do plt show. All right, I'm going to go -2 to -2. And so I have a function that has a clearly defined maximum. So the maximum occurs at 1, and the maximum value itself is 1. So I picked a function easy enough that you can just look at and determine what the function is. So the question is, if we want to maximize a function, how do we do it in Python? Well, the way it works with optimization is most optimization software is solved solely for doing minimization. So there is no function called maximize. There's only a function called minimize. And this is kind of standard in the optimization community. The key thing, what we can do is if we take this function, right, so we have 1 minus x squared, right, and if I just put a simple minus in front of it, what I'm going to do is just flip that function on top of itself. So I'm going to do the mirror image vertically. And so what I've done is flip that function. And if you look at it, the minimizer is at 0, so the same value as the maximizer. And then the minimum value is -1. So it's basically what this is hopefully showing you is that if you want to maximize f of x, that's equivalent to minimizing minus f of x. And so we can see this if I do sol is equal to minimize. And now what we're going to do is I'm just going to do lambda x minus f of x. So this is the function I'm going to, f is what I'm trying to maximize. So instead what I'm going to do is minimize minus f of x. And then if I just pick initial guess, I get 4. And then I print sol.x, and you'll see that I'll get back 0, right, which is the minimum value of the function, but also of minus f of x, but it's also the maximum value, or the maximizer of 1 minus f of x squared, or the f of x. So again, let me just plot this up, the original function. So I see I get the same minimizer, which is at x equals 0. And then if I want to look at the value, I'm going to just do minus sol.fun. So remember, sol.fun gives you the value at the minimum. And if I just put a minus at that, that'll give the equivalent, of the maximum value of the function. And I'll get back from that our minimizer, which in this case is 0. And then the maximum value of the function will be simply minus sol.f of n. And in that case, it's 1. So all you have to do is play this trick with minus signs with, to convert a maximization to a minimization. And so another way of doing this, if I want to do this with Markdown, I can write the formula that max of f of x is equal to whatever minus min of minus f of x. And so basically this is the trick. So max f of x is the maximum value of f of x. Well, that's equal to minus the minimum value of minus f of x, where the maximizer and the minimizer are both equal to one another, right? And we're just flipping that function around its vertical axis, right? So we have f of x here, and then I just flip it, and I get minus f of x. So hopefully that's clear. And because of this is why people only write minimizers, right? Because once you write a minimizer, you've effectively written a maximizer for your function. All right. So the other thing about optimization is I mentioned it's iterative and it's local. And so let's consider this function, x minus 1 times x minus 2 times x minus 4 times x minus 6. And so let's just print this function up. So I'll do linspace, I think maybe 0, I don't know. Do 0 to 10 and put 1,000 points. And let's do plt plot of x, f of x, line width equals 3, color, let's do blue this time. And then I'll do plt show. All right. Let me shorten up this so it'll be a little bit clearer. Let's go to 6. All right. So what you'll see in this function is we actually have two local minimums. So here's our first local minimum, and then here's our second local minimum. This minimum is also the global minimum of the function, right? Because this minimum is lower than this minimum. So local minimum just means like a little valley. But the way the algorithms work is basically if you start at this point, they go downhill until eventually they get the valley. So depending on this what your initial condition is here will determine whether you'll get this minimizer or this minimizer. So this is a local minimize. This is the local minimum of the function, and this is the global minimum of the function. And this is one of the limitations of optimization. So if I do sol.minimize, f, and maybe let's take our initial guess is equal to 0, right? And then I print sol.x, right? I'm going to get this minimizer here about 1.4. But if I chose my initial guess, say maybe if I chose 10, so I start like way out here, what you're going to find out is we're going to get this minimizer over here, which is 5.25. So depending on what your initial condition is, it's going to determine which of these two minimizers you're going to do. Way to think about it is, again, just you have a ball and you ask, which valley would it roll down? So if I start here, it's going to roll down here. If I start here, it's going to roll down here. And so typically when you solve a function using a minimizer, you typically have to guess, if you know that there's going to be lots of local minima and maybe only one global minimum, you have to play around with initial guesses, because depending on your initial guess will determine which solution you get for the function. So hopefully that's clear. So often what people will do is they'll use random number generators to do the guesses, and then maybe you'll run the optimizer 20 times, and then you'll try to figure out which of the minimizers from these random initial conditions give you the lowest value of the function. So that's kind of typically known as shotgun techniques in optimization, where you kind of hit it with lots of different initial conditions like pellets from a shotgun, and then you see which one of those initial conditions give you the kind of the lowest value of the function. All right, so this video was just pretty short. It was just kind of emphasize, how would you do maximization, and also how do you deal with multiple local minima. And with regards to the latter, again, you just got to try to guess lots of different initial conditions and hopefully find one that gives you a good minimizer of your function. If you have questions, please post in the comment section. And with that, I will end. Thank you.